Let's look at how to solve equations numerically. First of all, we need to introduce the sign change rule, which means that if a graph is continuous on an interval where x, say, is between p and q, and f of p and f of q have opposite signs, it means there has to be one root between p and q. So what are we actually saying here? So if the function is between x varies from p to q, and there's a y of x, you can see here the sign of f of p is positive, and here it's negative. So somehow the line has to cross, or the curve has to cross the x-axis, which means that y equals 0. So there's a root. If the sign changes going from p to q, there has to be at least one root there. There could be more, we're not sure. Here's another example. It doesn't matter if y starts negative and goes positive, or if it starts positive and goes negative. And that's what the sign change rule basically encompasses. Here's another example where you can see there's more than one root. Somehow it's going from positive to negative, but like I said earlier, who says there's only one root? Here's two roots. There's a double root over here, and another root, and then here's three roots. So we can use the sign change rule now to be able to find roots, and this leads into the next methods. Before one can use the sign change rule, it's useful to be able to plot to find more or less where one would see, where must you start looking where the sign changes, where y changes. Here's just an example. Y equals x to the 3 minus 3x minus 5. It's difficult to find the roots of a cubic equation, but it's very easy to find the roots of a quadratic equation. And if we differentiate, that's what we get. So we get y dash equals 3x squared minus 3. And if we set that to 0, we can find the min-max of our cubic equation over there. So first of all, differentiate, and then find the coordinates of your min-max. So we've done that now, so you can see y dash equals that. We can take out the 3, get rid of it because it's equal to 0, divide by 3 on both sides, and we get simply that the equation reduces to x plus 1, x minus 1. So the positions of our min-max are at x equals 1 and x equals minus 1. And we find by putting 1 and minus 1 into our equation, we can find out where these min-max are. So I'm going to just draw it here. Imagine that's minus 1, and that's 1 over there. We can say, okay, for the first point, we had a min at minus 3, and the next one at minus 7. And we can see from our c value, which is always useful, that it intercepts at minus 5. So we can put a minus 5 here. And now, because it's a cubic, we know that, and because a is positive, there's a positive coefficient on x to the 3. If x gets very big, the thing becomes positive, very big positive. So we're going to end there, and we're going to start here. And there you have your graph. Okay. So this is my max, a local maximum over there, and there's a minimum over here. And we can see that our root is somewhere over here. And by trial and error, we can now find, we can put a value there, and we can say, right, when x is equal to 1, the function is negative. Maybe when x is 2, it becomes positive. And we could then search where our root is between these two numbers. So let's move on now and use the sign change rule in a decimal search. The decimal search is a method used to find a root. Okay, in this case, we're going to use the same example that we've used the sign change rule for. And we can see that y of 2 is minus 3, and y of 3 is 13. So we found out that there's actually a change in sign of y between the numbers 2 and 3. So x is going from 2 to 3. So let's just draw that quickly. So we've got our graph there, we've got a number 2, and we've got a number 3. Okay, it's not to scale, sorry for that. There's y of 2 is minus 3, and y of 3 is 13. It's always good to draw it roughly to scale. Okay, now you can see that the root is sitting kind of, we would expect it to be closer to the 2 than to the 3. So it's always good to just draw the thing more or less. It helps to narrow down the search. You can see now there's a sign change between the numbers 2 and 3. And now if we look, let me just put that over there. So if we try different numbers now, we try a y of 2.1, y of 2.2, y of 2.3. And we can see when this becomes positive, as we're going closer and closer towards the x-axis, when it becomes positive, we know the sign has changed, and we can say, okay, the root lies between maybe 2.2 and 2.3. So we've actually narrowed our root down to one decimal place. And then we can take it further, and we can narrow it down to y of 2,21, 2,23, 2,24. So you can see that's why it's called the decimal search, because we first find, say, the first decimal point, the second decimal point, and so it goes. The trick with the decimal search is to know when to stop. If we're required to find the root to 2 decimal places, okay, and a sign change is found between, say, 2.13 and 2.14. So let's see, we've got here, we've come here, there's 2.13, and there's 2.14, okay, and we've drawn it roughly to scale. We say, okay, you know, we expect the root to be somewhere there. But we're not going to guess and say, okay, it's 2.13, because who knows, maybe the curve does something like that. You don't really know. So what to do, if you get an exam question that wants it to 2 decimal places, and you know what it's between, you know it's 2.13 to 2.14, all you need to do is find the midpoint here, which is 2,135. And now you can say, right, 2,135, if he's positive there, then we know the root lies somewhere between 2.135 and 2.13, so round it off, it's going to be 2,13. On the other hand, if the root's still negative, you're going to see the root is on the upper half. So then the answer would be 2,14. So it's useful to be able to just nail the answer at the end and be able to know exactly which side it falls. And you use that midpoint there to be able to do that. Don't go now and look for the third decimal place. Okay, it's not necessary. You don't need to go 2,131, 2,132. Rather, just go to the midpoint. That's 2,135, and then see which side it falls on. Because you weren't asked to find it to the third decimal place. A key concept of the decimal search method is that you'll be given an expression that's equal to 0. Okay, you've been asked to find the roots of an equation. But in order to try different values, you need to set that expression equal to y. So then you try for different values of x, what do we get? And we narrow down y until it's as close to 0 as to be able to give us that accuracy that we're looking for. So always remember, if the equation is equal to 0, you need to introduce a y. Now this is very contradictory to what we normally do. Normally you're trying to solve a y and get rid of variables, but in this case you're actually introducing a variable. And it's just a slightly different way of thinking when we're narrowing down that search. So just bear that in mind. The key to using the decimal search method is to find 2 x values where the y transitions from being positive to negative. And to do this, one needs to do a little investigation and also sketch the graphs. So here's an example of finding a root using the numerical method. X e to the x equals 1. Now this can be written as x e to the x minus 1 equals 0. And if you want to find the roots of that equation, or e to the x minus 1 over x equals 0. That was obtained just by dividing that equation by x and then moving it across. And then finally by taking logs on both sides, or actually by dividing by x and then taking logs, you get x plus ln x equals 0. Okay, so let's try and draw the first one here, x e to the x. Let's look at that composite function. First of all, if you draw y equals x, that's a nice straight line, easy to do. And if we plot e to the x, we get that. We cut through at 1. Now you can see we're interested in x times e to the x, and if you times those two, you get a 0. Okay, and then you're going to drop it down by 1, okay, because it's minus 1. So my curve is going to go through that point there, and as it gets big, x times e to the x becomes a very big number. So you can see it's going to have this upward, it's going to be moving upwards from there. So you can see the root is somewhere to the right of the y-axis here. If you put x equals 1 into your equation, you'll see that it's positive. So the root, okay, even when you've minus the 1, you're going to find the root is somewhere between 0 and 1. Okay, because it's if you put x equals 1 in this equation, it's going to be 1 e to the 1, which is 2,71 minus 1 is about 1,6. So you can see how at x equals 1 you've got a positive. And now you can use the decimal search to find your root between 0 and 1. If we looked at the other equation, i.e. e to the x minus 1 over x is equal to 0, or e to the x equals 1 over x, if we plot that, we see here's the e to the x, boom, and we can draw 1 over x. And we can see at some point these two meet. Okay, there's your 1 over x, there's your e to the x, and you can see that you're going to get that root somewhere on the positive side. If x equals 1, okay, then e to the x is e, just e, and 1 over 1 is 1. So you can see how at this point the e to the x is bigger at 1. So the root is lying somewhere between 0 and 1. Okay, now you can do your decimal search, because you know there's a sign change in that interval between 0 and 1. So the decimal search method is one numerical method. Another one is finding roots by iteration. This is really a cute method, and I enjoy it very much. So for example, if we use our expression that we have been using, if we rearrange the terms and put the most dominant one in the front as the subject of the formula, we get x cubed equals 3x plus 5. We can now cube root both sides, and you get left with x equals the cube of 3x plus 5. Now, if we take any value of x, let's say we start off with x equals 2, and we put that into our expression here. We say 3 times 2 plus 5, and we cube root it. We get a value of, we call that the next x, so it's xr plus 1. Okay, so in this case you would have got 2.2. Now you put 2.2 into this expression and it spits out 2,26. So slowly but surely it actually converges to an answer, and that is the value of x that satisfies this expression. Now this seems like magic. How does this actually work? First of all, for it to work in general, okay, not always, it takes a bit of investigation, but start with the most dominant term, your x to the 3, and put that as the subject of the formula. That's the first tip in using this method. So let's see, how does this actually work? Okay, so I've written my function down. I've got my function over here, and I'm going to draw, let's just draw some axes and see what a typical curve might look like. Okay, since we've got x on the left-hand side, we can plot y equals x. That's nice and easy. And then we've got some sort of complex function. Don't worry too much about the complex function, but I just want to let's draw some sort of function like that. And where the two meet, that's the value of x that we're looking for, where the condition is satisfied. So let's say we were to pick any value. Let's say we say, okay, we're going to pick x over here. So let's say that's 1. Now, we put 1 into our complex equation, and we get a y value. Okay, there's my y value. But that y value, if we look here, now moves, that is now also my x value, because this is my y equals x curve. So the y value that results from my function now becomes my x value, which I put back into my complex function. So now my function's moved a little bit closer to where these two are going to meet. Now I work out a y value, but that y value becomes my x value. Okay, here's my new x value. But now I put my x value into my y, and slowly but surely I'm moving closer and closer to the actual root. What's interesting is it doesn't go past this. It actually narrows down more and more and more, because if you were to move in the other direction, let's say you picked your answer, say x equals 3, and it's above where my root is. If I put 3 into this complex equation, I get a y value, and then I use that y value, now y equals x, see there, y equals x, and I use that one now as my new x value. I put it into my complex equation, and it moves closer again. So isn't that amazing how it moves towards that root? Okay. Now, it's not always that simple. Sometimes you get a divergent result, okay, where when you put in x, it actually moves away from the root. Now, when would that happen? So let's say we made the 3x as the function, okay, as the primary function, and we took the x to the 3 on the left, and we said x equals now 1/3 of that complex function on the right hand side. Okay, we're doing the iterative method, so we've got a y equals x, but now my graph would look something like this. It's getting bigger and bigger. So now if I try a value, let's say I try a value here, I try a value, I put it into my complex equation, I get a y, and that y I use in my x. Okay, you see how I've moved away from the root now? I started over here, and now the x value is used again, and I'm moving further and further away, and I'm not going to converge, or if these two intersect in more than one place, I could end up converging to another root. And it's important to spot that. Sometimes you think there's a root between the numbers, say 2 and 3, but then your thing's converging towards x equals 5, then it's converging to another root. Or maybe it's not converging at all, it's just getting more and more out of control. Okay, if I picked a value here, I picked the x value over here, I would have seen, okay, put that into the complex function, and we get a y value, we use that y value into the x, and now we're going further and further away from our root. And that would be a divergent root. This one might be an example of converging onto another root, a different root to what we expect. Okay, so there's a lot of little nuances with the iterative method, but it's a very useful and easy approach. If I go back now to this function, just a little tip here. When you put your equation in your calculator, put everything there and use the first value of x, then you must just recall the formula on your calculator. Don't type this formula over and over and over. You won't have time. You need to put the next x value into your answer just by editing the expression. So just get the hang of that. Practice that a few times as you go around. Try it on this example that you can quickly put the next value of x into your expression in your calculator. It's very important that you're able to do this quite quickly. What have we learned? What must you know? Well, first of all, there's the sign change rule. Now, the sign change rule is used as a feeder to the decimal search. They are always going to ask you to find a root between 2 points and lead you into the decimal search, if that's going to be part of the paper. So the sign change rule and the decimal search go hand in hand, okay? And that just means that if there's an interval on a graph between where x is between p and q, and f of p and f of q have different signs, well, there has to be at least one root between p and q. And now you can narrow down your p and q until you have an answer that's to the required degree of accuracy. Okay, so that's the sign change rule. The decimal search, you use the sign change rule, narrow it down, and there you go. Okay, a tip with this decimal search is they give you an equation equal to 0. You change that equation to equal y, and you see where is y changing sign. Okay, very unusual to introduce a variable, but that's a key to how this method is used. So just be aware of that. And then finally, my all-time favorite, finding roots by iteration. You rearrange, putting the most dominant term as the subject and just inverting its function. So if it's like e to the x, you'd make it a ln x on the other side. So you make x equals some complex function, and then perform all your iterations and check if it's convergent. Now, if it's not convergent, try making a different expression. So x equals a different expression. Obviously, the term that you thought was the most dominant isn't. Then pick another term and make him the subject of the formula. Okay. So thank you very much. If you've got any questions, please feel free to email me. I'd love to help you if necessary. Yeah, and if you've got any comments, most welcome. Thank you very much for listening. Cheerio.